All right. So today we are going to discuss that is some steps which we usually use when preparing data for linear regression. Okay. Then after that, we shall now that is do that is a simple that is linear regression. Okay. So with that, we are going to that is under linear regression. We are going to use um, three methods. Okay, that is using the linear that is trend line. Okay, to determine the equation of the line. Also, we are going to use the analysis tool pack. Okay, for us now to do what to do that is to do the linear regression, and also we are going to use that is formulas that is also to perform the same. All right, good. Now let's start with the preparing data preparing process. So that is linear is it's been studied at great length, and there is a lot of literature on how your data must be structured to make sure that is we use or we get the best model. So we have a lot of what that is data restructuring. Okay, we will discuss different steps. Okay, and these steps we are the first step is linear assumption. Before we can that is start our linear regression that is a process, or before we can start even building a linear regression or building a model. Okay, we have to choose well our that is our independent variables. Okay, like we have to assume that is or it is a must the dependent variable and independent variable to have what to have a linear relationship. That is, we need to have a linear relationship between the input and the output. Okay, and remember we say that our output it's what we are trying to predict, that is y, and this in this case the x or xi's. Okay, it is what our independent variable or the inputs. Okay, we can say they are the inputs. So linear assumption, the linear regression assumes the relationship between what your input and output is what is linear. It does not support anything else. Okay, so it does not support anything else. And in case maybe we don't have any that is a linear relationship, then we might need to do what to transform our data to make the relationship to be what to be linear. And what we can do, like for example, if we add that is an exponential relationship, okay, then it will mean that we will have to do what? We will have to perform log normal, okay, for us to do what? For us to get that is to get a linear relationship. Like for example, if the equation is like this, that is y is equals to a raised to x, okay, plus c. So with this, you can see it is not ax, rather it is a raised to what? To x. Okay, so we will have to do what? What we call log transformation for it now to be a linear relationship. So we'll say like if we insert log, that is log here, and also a log here, and also a log here. Now these will what? Will now come down and like for example, if now we use what log, it will be like this. So it will be log y will be equal to x log that is log a plus log what? Plus log c. So with this, you can see now we have expressed now our that is our equation to be what? To be to have or our two variable, that is x and y, to be what? To be linear. Okay, because now the log of a will be a constant. Okay, and also this will be a constant. Okay, so with that we can do what? We can also do some transformations. Okay, log no that is log transformation is one of the what? Is one of the examples. Then we have that is removing the noise. Okay, so that is linear regression. Okay, basically noise means outliers. If your data has outliers, then you will need to do what? To do away with outliers. And remember we say that outliers are what? Are the extreme values. Either it can be extreme small or extreme big value. Okay, so for us we have to remove what? The noise. The noise in this case, they are the outliers. So linear regression assumes that your input and output variables are not noisy. Okay, consider using data cleaning operations that let you better expose and clarify the signal in what? In your data. The most important for the output variable, and you want to remove what? The outliers in the what? In the output variable y, if possible. Then we have remove collinearity. Like for example, uh, if you are independent variables, that is this majorly applies when we are dealing with what? Multiple linear regression. Okay, yes. So in case your independent variables are that is are highly correlated, then you will need what? You will need to remove the collinearity. Okay, and with this will be that is will be the so we will be solving the problem of overfitting. Okay, yes. So linear regression will overfit your data when you have highly correlated input variables. In this case, input variables, we've said they are what? Input variables, we've said they are, that is, they are the independent variable, okay? The x variables. Then you will have to consider, that is calculating pairwise correlation for your input so that you may know that is the most correlated what? The most correlated independent variables, and then you will be able to what? To remove them. Then we have Gaussian distribution. Okay, so under Gaussian distribution, we usually say that for linear regression will make more reliable prediction if your input and output follow a Gaussian distribution. And a Gaussian distribution is what? It's a normal distribution. Okay? It's a normal distribution. And we'll learn more of what? Of the normal distribution when it comes to what? When we will be discussing distributions. So linear regression will make more reliable predictions if your input and output are that is follow a normal distribution. You may get some benefits using transforms like the log transform and also these box clocks. Okay, I've never come across this transformation, so maybe you can look that is on it and see if you will have some ideas that is about that. Okay, yes. Then we have now rescaling of the inputs. Okay, rescaling of the inputs. So for linear regression, we'll often make more reliable predictions if you rescale your input variable using that is standardization or normalization. Like for example, rescaling the that is the inputs. It's basically in this case now we are talking of the that is the constants. You remember the way we said about enhancing that is performance of a model, and we say that for the performance we can do what? We can enhance the performance by that is optimizing, okay, by optimizing our constants. Okay, yes. So with that you can always you can use different methods of optimizing the constants, okay, so that we may get what? We may get the best model. So those are the major that is processes which we usually use, okay. So we are still going to use the umbrella cells data. You can open that data so that you may do that is the practicals. Okay, I will take it that is slow now when we are doing what? When we are doing the practicals. Okay, and I have said we have three methods. Okay, just a minute. I've said we have three methods. The first method is what? Using a regression line. Just a minute. Using that is a regression line. Okay. And then the second we have that is using analysis tool pack. Then the third one is what? Using inbuilt Excel functions. Okay, yeah, so these are the methods which we'll use to achieve what? To achieve that is the same objective. Okay, but for maybe for your work to look more good and also to look more analytical, I usually prefer that is this method using analysis toolpack, but we shall check on that. Okay, yes. So in our that is the first thing is that is to check the data and see if we have what? If we have outliers. Okay, so what I'm going to do, I'm just going to copy that is the first column somewhere and see if we have outliers. Okay, I'm going to sort that maybe from the smallest to the largest, and I can see we don't have outliers. Okay, because we have some consistency in the difference. Okay, in the difference between what? Between that is the values. Okay, we have consistency. Okay, between what? Between the that is the values. Yes, we have some consistency between the values. So I can say that is in our case, we don't have what? We don't have any, that is, we don't have any outlier in our data. That is in our rainfall data. Okay. What about the umbrella cells? Maybe we might have that is a month where we had like an hike, So the same here, I can see the increase. It's something which is small and notable, not exaggerated. So we are good. We are good with that. Okay, I'm good with that. So still the umbrella cells data is still okay. Okay, so no outliers in our data. Okay, so there is no need to remove what and that is outliers because we don't have them here. Okay, all right. Anything else? That is the normal distribution of the data. Let's try and see if we have that is it assumes. Okay, it is not a must to be exact. Okay, but at least I can see. You can see from the that is the scatter plot. You can see we are having what? It is assuming these are like. Let me just highlight one year. Okay, if I highlight the one that is only 1 year, you can see this is almost that is following a normal what distribution. If even though, okay, even though that is it's not that exact, but I can see at some point it is what it is following a normal distribution. Okay, what about this? Let me also check that. Yes, the same. That is the same to that. At some point, it is tends to what to follow a normal distribution. So with that, that is the this assumption odds. Okay. Then for that is to remove that is noise. Yes, we've checked. Let's now come here where we remove them. That is collinearity. But in this case, we don't need to remove collinearity because we only have what? One independent variable. Okay? We have only one independent variable. Okay? Yes, so there is no need for that. Otherwise, I want us now to go to the first step, okay, and pay attention on this and make sure you follow, okay, make sure you follow on this. So the first thing is to highlight your data, okay. You can highlight your data, okay. That is together with what? Together with the columns, right? Are we together up to that point? All right. Then, after you highlight the data, go now to we need. Someone has raised. Yes, Kwamboka.
Yes, when I select my data, when I highlight the data,
Mm-hmm.
uh, and okay, I'm not really able to see how you can see that graph. You see, when you highlight your data, there's a graph already that I can see,
Yes,
but on
it's
my side I can't
because
see that.
maybe it's because you have highlighted even the years. Don't highlight the years. Just highlight from the what? From the month. Okay.
Mm-hmm.
Yes,
Okay.
just highlight from the month and see. And then for this case, we need what? A scatter plot. We will need a scatter plot. Okay, that will give us what? That will give us that will give us the scatter plot for our what? For our data. So you can always start with the recommended, okay, and see different distributions we have of the what? Of the data. All right. But for our case, we are that is we are our objective is to go to the what? To the scatter plot. So go to the that is all charts. Then go to scatter, all right, and a scatter, and a
Still
scatter.
inactive. I don't know why.
Okay, maybe are you in a position to share your screen?
Let me see if I can share.
So you can just say that, and then when you are ready to share the screen, you will let me know so that we may check the problem. Okay. So of course, why do we need why a scatter plot? Okay. So the scatter plot will give us that is a good visual of our data points. Okay, we will be able to see what we will be able to see that is how our data points are distributed. Okay, and in that case, I won't go with the first scatter plot because the first scatter plot is kind of showing me the trend. Okay, you can see it's kind of giving that is giving me the trend. Okay, but now I want to plot what that is the umbrella cells against what the umbrella cells against the rainfall. So then the second scatter plot will satisfy what will satisfy that is my need. Okay, like for example, if I highlight this data point, okay, if I highlight this data point, you can see that is over the data point. Okay, you can see we have some coordinates here: 146.3 comma 43. Let me just that is increase this so you can see this data point. Okay, let me just highlight this data point. Yes, so on this data point you can see we have what we have 146.3, which is now our what the amount of rainfall, which is on what which is on our x axis. Remember, the amount of rainfall, it is what it is the x axis, as we had said, because we are trying to predict the umbrella cells. So you can see the coordinates is x comma y. Okay, whereby y it's the number of what it's the number of umbrella cells. Maybe we can include that is we can include the axis so that we may what we may have that difference. Okay, so to include the axis, you'll just go to this plus which is on your graph. Okay, we have this plus, then under this plus you can select what we need that is the axis titles. Okay, just click axis title and then you can come here and edit. Here we need this is our rainfall in millimeters, and we also need what we also need this is our that is umbrella cells, umbrella cells. This is our umbrella cells. Okay, good. So with that you can see now we can now plot the line of best fit here. Okay, we can plot the line of the best fit on this. Okay, yes, so to do that, all to that is to draw the line of best fit, you will come as well to the that is to the plus. Okay, then go down to trade line. Okay, there is an arrow after the trade that is on the right side. Okay, click that arrow, and we need linear, we have exponential, we have linear forecast, we have two what 2 period moving average, but you can go to more options. I want you to go to more options. There is a reason as to why, because I also need us to that is also to display or to input the what the equation of the that is the equation of that is the equation uh, of the line. Okay, so with that of course we will need what a linear, will need a linear trade line. Then we will need what? The equation of a straight line, okay? And you can see, okay, just a minute, want to go back to the options, trade line, okay, more options. So I will check what? The equation of baseline, and also I will need what? To display the r squared value. Okay, so remember the r squared value, what I told you it is called the that is coefficient of determination. Okay, so that is the coefficient of determination helps us to do what? Helps us to evaluate our model, to see how good is our model. Okay? Yes. So with that, um, now here, I can just remove this one. So now here we have the equation of that is the baseline. Okay? Or I can call it now the model. All right, and then here we have what we have that is the performance. Okay, the performance of our model. Okay, so now I want us to interpret this. You can check this value. Okay, so let's create a model out of what? Let's create a model out of our that is of our data. Just a minute. And I hope we are all together and you are following. Okay, if we are together, can you indicate on the chat area? Someone has raised their hand. Yes, Kwamboka.
It's me again. Now, I did not see how you got that coefficient of what something you have said. I didn't see
Of
how you got it.
determinations. So of determination, did you manage first of all to plot the graph?
Yes, I managed.
So to get the coefficient of determination, which is this value, go to this plus, okay, trade line, click this arrow after the trade line, go to more options, okay, and select display the equation of chart or on the chart, and also display the r squared value on the chart, and you will see them.
Okay, when I click on both,
Mhm.
I'm not able to click both of them. When I click one, the other one is not selected.
Can you share your screen? I hope we are all together. If we are together, can you respond to the chat area?
See, when I click here, like equation, display equation on
Yes,
chart.
and also there, yes, that way. And then you can now close there, where we have format trade line, and you'll see now the equation and yeah.
Okay, thanks.
Okay, you can drop from screening. Okay, I can see only 4 people who we are together. Uh, Gertrude, we are together. Salome, we are together. Simiu, we are together. Claire, we are together. So it seems the others we are not together. Okay, that's okay. So now I want to illustrate something. So Claire, no, Kwamboka, give me that is the equation of straight line that you got. It is y is equals to 0. Kwamboka.
Y is equals to 0.4482x minus 18.915.
915. Let me confirm as well. Yes, I got the same. All right. So now I want us to transform this that is model. Remember, we need what? Umbrella cells. Okay, and we've said our umbrella cells will be given by a constant. Let's call that constant A, multiply by, that is the rainfall amount, okay, plus or minus another constant, let's say C, whereby this is we say this is the slope of the best line feet line, and C, it's what? It's our y-intercept. Okay, so basically this model is represented here. Okay, why? Because we have y, which is our umbrella cells, will be equal now to 0.4482x, okay, then minus, remember this is x is what? It's our rainfall, minus 18 point what? 18.915. Okay, you can check that. So, like for example, let's now go back to the Excel. Okay, let's assume now here we have our what? Our y, all right, and we have what? We have hex. We have constant here, that is which is our m, and we have what? We have our x here, and we have our c here. Okay, so now we have the value of what? We have the value of uh, the value of our m. Okay, so our m is 0.4482. Okay, we don't have the value of what? We don't have the value of x, and we have the value of what? We have the value of that is of our c, which is, let's say it is 18 negative 18.915. Okay, so you can see we have those two values, but we don't have what? We don't have y, we don't have what? X. Okay, so let's assume maybe we want to calculate for what? For, that is for y. So this will be equal to, okay, why we said it is mx, which is m, we can maybe put brackets, which is m multiply by x. Okay, then we can plus, because it's always plus or minus. Okay, so if we plus, remember that is plus or minus will be that is minus, plus or plus minus will be what? Will be minus. Okay, so we will get a value, that is what we are trying to predict. Okay, so maybe let's assume we know the amount of rainfall for the, that is for this, for the next what? For the next year, that is, let's say this is 2018. Okay, let's assume this is 2018, and in 2018 January, maybe we what? We will, or we are assuming that we are going to receive what? This amount of rainfall, that is 0 point that is 0 point sorry, 105.6. Okay, so our x here will be that is 105.6 for us to get maybe the number of umbrellas which we might we might sell during that period. And here it is going to give us that is an approximate value, okay, with that is with plus or minus, okay, plus or minus 5, meaning it can go maybe more. For your model, we allow it to predict plus 5 or plus what, or minus 5, sorry. Like for example, if we predict this, okay, 104, remember under 104.6 we got that to what, that to that is 32 umbrella cells, okay. So with this formula, if we use this 104.6, we might not get what, we might not get the exact 32, okay. That's why we usually give that is an error term of plus or minus what, 5, okay. So we should be within plus or minus 5, meaning our model will be 90 what, 95% accurate. Remember, it's not easy to get a 100% that is accurate model, that is accurate model. So in our case, even we can see we will have that is an error deviation of, let's say it will be equal to 1 minus 0 point this performance, because this model is 91.76% accurate, okay. So I want us to see maybe let me do a percentage. So our error term should be that is 8, that is plus 8 minus 8, okay. It should be within plus 8 minus 8. Why? Because our model is 92% accurate, okay. So like for example, let's take an example of this. We need what, we need to see if our prediction is accurate. So you can see when we predict the same number of umbrella, we are not getting that 2, rather we are getting 28, okay. So you can see still within what, plus or minus 8. Why? Because it will be less by, that is it is less by minus what, minus 4, all right. So if we want maybe to predict the amount of rainfall in this month, now we will say that is the x value we need to be equal to the amount of rainfall assumed in that month. And you can see we are getting almost the same almost the same value, okay. What if maybe we get 118? If we take 118, you can see we are getting what, we are getting 33. Here we are getting 34. Let me make this to be that is to be a whole number, because umbrellas, we don't have that is a half umbrella, okay. So under this you can see when we use now 118, okay, we are getting what, we are getting 2 less umbrellas, meaning it is still within plus or minus what, 8 umbrellas, meaning we are still okay. Why? Because our model it's 91.76% accurate, okay. And this is how we predict, okay. So like for example, if we were to predict for the umbrella cells, okay, let me assume, let me take all this, okay. So let me take this formula. I'll take this formula where, here, Okay, and I will change just a minute. We have a constant here. I can just include, let's say, m and what, and c here. So under here we need what, the number of the umbrellas. Okay, so this will be equal to just a minute, I need these constants here because these are constants, they won't change. Okay, so in this will be equal to we are creating a model here, that is, it will be now, that is our, the number of umbrellas will be now mx plus or minus c. Okay, so it will be into brackets this, and since this will be referencing this, we can do what, we can lock that cell. Okay, we can lock that cell, multiply by this cell, okay, comma, which is varying, then plus this cell, and then we can do what, we can log the same, since we will be what, since we'll be referencing to that cell. Okay, and then click OK. So with this now formula, we will be able to what, we will be able to predict the that is the number of umbrellas, the umbrella cells. Okay, given what, given a forecasted that is amount of rainfall. Okay, like for example, if I take, let's say, let me just take these values. Okay, and say maybe the amount of rainfall will also that is collected in what, in 2018. Okay, yes, and see the, that is the what, the umbrella cells. So with this you can see we have now the what, we have now the umbrella cells. Okay, you can see we have the umbrella cells, and we can try to check the deviation. Like for example, we have this deviation here, this is for the predicted that is data. Okay, this is for the predicted data, and this is for the actual which maybe had happened. Okay, and see the variation. I want us to check the what, the variation. Okay, so with this will be equal to we should get the actual minus what, the predicted. Or no, it should be the other way around. We should get the maybe let's take the predicted for it to be, to make sense. Okay, yes, not to confuse you. So with this you can see our model predicted what, predicted that is three more umbrella cells in this that is in January of what, of 2018, with the same amount of rainfall as it is in January of 2016. Then you can see that is for the February. You can see our model forecasted two less, okay, umbrella that is cells with the same amount of rainfall as what, as it in February of what, of 2016. So you can see we are within the range, plus or minus 8. Okay, in fact our data it's within plus or minus 5%. Okay, or plus or minus 5. Okay, so you can see our model that is is still accurate, though not 100% accurate, because it is not easy for you to get 100% that is model, but you can get 99 percent model. You can even get 99.98% model, but you can't get an 100% model. Okay, even in research work, okay, even in research work, the level of confidence, okay, of the research work for the normal research work should be what? 95%. That is your research work. It should be statistically significant, or we should have that is confidence level of 95%. That is for normal research. Then for medical research, we should have 99%. Okay, it should be 99%. That is confidence level. Okay, we cannot get more than what? We cannot get more than 90. That is, we can't get 100% confidence. That is level. Okay. Yes. So that's how you can create maybe a predictive model. There is also other formulas. There is also other formulas which can be used to do what? To do that is prediction. Okay, like getting what? Using the trend. We have the trend formula. We have forecast. That is formula. Okay. Yeah. So we have these formulas. You inbuilt functions. You can go and what? You can go and try to and check if you can do what? You can get this. Like for example, if we use the trend formula, okay, you can see we need what? We need the data from the non-wise, whereby the non-wise are the what? Are the two, that is they are the what? The non-wise, sorry. The non-wise, they are the umbrella cells, okay, for the past 2 years since we know them. And then we have what? What? Non-axis. Non-axis, of course, they are also the what? The x values for the previous, or for the previous 2 years, and then the new axis, they will be now the new value of what? Rainfall. Like for example, if I do that, I'll take this. Okay. Then comma, we need what? The non-axis. So the non-axis will be same as this. All right. And then we need what? The new axis. Then you can check this new axis. Okay, and then since we will be referencing to this, we will have to do what? We will have to lock this, that is these cells. Okay, we'll have to lock these odd non values. Okay, we'll have to lock them. We'll have to lock them. We will have to lock them. Okay, and then close and then run. So if you run, you can see we are getting what? We are getting almost the same values. Okay, the ones we got when we were what? We projected that. Okay, maybe let me do the same here so that you may see that we are having the same values. So we have M and we have it was C. So the M was 0.4482. Okay, the C was minus 18.915. I guess so. Yes. Now I want us to maybe now to forecast, okay, using our model and see if we when using the trend line we are getting what? We are getting the same value. So it will be equal to um, All right, should be mx plus c. So it will be m multiplied by our x, which is this. We can put this into brackets. Okay, then mine plus this. Okay, and with that, we will have to do what? We will have to, that is to lock E27. We'll have to lock these cells. Okay, then we'll also have to lock this one. So if we lock that, then let's keep this to be a whole number. You can see we are getting what? We are getting the same values. Very accurate. You can see we are getting the same values, meaning that is our prediction. That is our prediction. We've done them. That is correctly. Okay, we've done it that is correctly. We can also use another formula known as linear forecasts. Is it okay? Forecast dot linear. Let me check. Yes, you can see now forecasts. We have this formula known as forecast.linear, or it's a linear forecast. Okay, we have the axis and we have the non-y's and non-axis. Okay, so we'll start with the what? With the x, comma, then we'll go to the non-y's. Okay, as the formula tells us. So we will highlight what? We will highlight the non. That is the non y's. Okay, then comma, we will need what? The non-axis. We will also need the non what? The non-axis. That way. Okay, and then we can close. Okay, this cell, I want to format it as what? As value. All right. So you can see we are formatting it as a value. So what we are going to do, we are going to log what? We are going to log these cells for the non-wise and non-what? For the non-wise and non-axis. This is, it's in fact, it's just a confirmation. Okay, it's just a confirmation if if what we get with the model which we created, it's the same we are getting with what? Excel inbuilt functions. And you can see we are getting the same values. Can see we are getting the same values. So when we use the thread function and when we use the linear forecast function, okay, so we are almost getting the same thing. Are we together up to that point? Are we clear?
Yes.
All right, good. Good. Now we are done with the first step. Okay, we are done with the first step. So basically, the first step using regression line, it gives us the equation, okay, or it gives us the model, the value of constants, okay. Then and that is r squared. Okay, we also get r squared, and r squared here it's the that is a coefficient of determination, and it shows us the what? The performance of the model or the accuracy of the model. Like for example, we can say that our model it's 91 or 92% accurate. Okay, depending with what? Depending with the that is depending with the uh, with our computation. All right. Then also we will also discuss another one known as adjusted R squared. But for the adjusted R squared, it's majorly used when we are dealing with what? When we are dealing with multiple linear regression. It is said to be more accurate. That is, adjusted R squared is said to be more accurate for multiple uh, regression when we are using or when we are doing multiple linear regression. All right, that was our first that is method. So the second method is what? The analysis using of the analysis tool pack. Okay, now for the analysis tool pack we are going to do it, and then tomorrow we if not tomorrow, on Monday we'll discuss what? We'll discuss or we shall finish with the what? With the findings. Okay, yeah, but I can roughly maybe explain it and then explain in depth on Monday. But as well, I have shared that is some notes which I prepared. Let me check if I shared those notes. I have some notes which I shared with you. Yes, there is a PDF which I shared with you, and this PDF will give you that is all those all those steps which we have what we have used when it comes to linear regression. Okay, all the examples which I showed you. And now we are going to do the analysis toolpack. It has even all the steps which we've done, okay, except for the confirmations which we were using here to confirm. You won't get this that is on the notes, but we have that is now we have the interpretation here. You can go and also check on the interpretations. Like we can see the multiple R. Multiple R here we are say it is basically the correlation coefficient. R squared, as I have told you, it's the coefficient of determination. We have adjusted R. Mostly I've told you we use it when we are dealing with multiple regression analysis. Then the standard error. The standard error, we talked about the error term yesterday. Okay. Then on Monday we shall discuss on the ANOVA. That is the analysis of variance. Okay. Like for example, what significance F means. Okay. And how can we compare the significance F with what? With the p-value. Okay. Remember the p-value, we usually use it to do what? To check if our model is statistically significant. Okay, and p-value is always that is 5%. So if we get a significance F which is less than 5%, then we say our model it's okay and it is reliable. We shall discuss all this, but first of all, let's do now what? Let's now do that is the practical part of it. Okay, so with that, now we are going to use the analysis tool pack. So you will need to go to data, then go to data analysis. Under data analysis, go to regression. Okay, click regression, then click OK. Then we will need the input range. Okay, the input range y and the input range of what? Of x values. Okay, so let's start with that of y. So for the y, we are going to take the 2 years. So you are going to highlight the data only up to that point, the 2 years. Don't exceed that. Then let's go to x. Also highlight the x data. That is up to 2017, because for the 2018 we just did what? We just computed. And then confidence level, since we are doing that is this is a normal or a general research work or analysis. Just we will use confidence level of 95%. Okay, if it was data related to medical data, we could have used what? We could have used 99%. Okay, then we need what? The output range, because my worksheet here, it is busy or it has been used. I can go to new what? I can go to. I'll just go to new worksheet. Okay, just click new worksheet and then click OK. Once you click that, it will now give you what? An analysis. It will give you an analysis. As simple as that. Just imagine. As simple as that. And we can check. Okay, we can check if we got what? If we got the same values as the first method. Okay, you can see the first method we got what? We got 0.4482 and negative 18.915. Okay, and then coefficient of determination of 0.917. Okay, so let's start with the coefficient of determination, which is r squared. You can see we've gotten the same what? We've gotten the same value. Okay, then for the coefficients, you can see we've gotten the same coefficient for x variable, and the what? The intercept, we've gotten what? We've gotten the same value. Okay, so you can check we have the same what? We have the same value. All right, so meaning that is the two methods we've gotten the same what? The same value. So now let's come to, I'm going to interpret, or I'm going to interpret the first what? The first or the summary output part, and then next week Monday we shall do what? The ANOVA part. Okay, let's now finish this. So multiple R, basically it's the that is coefficient of correlation. Okay, remember we did the correlation of what? Of our data. So like for example, let's do the correlation of this data and see if we are going to get the same value. So we are going to say correlation, correl, that is correlation. Then we need what? Our arrays. So we need this up to December of 2017, up to that point. Okay, then comma, we also need correlation of these parts up to that point, and see if we will get the same value. You can see we've gotten what? We've gotten the same value. Okay, meaning this multiple R, basically it's what? It's the correlation between our two values. Okay, yes, so you can see out of the correlation, that is our two variables are highly correct, that is correlated. Okay, meaning an increase in one value will what? Will also lead to increase in the other value. This is a positive what? It's a positive correlation. Okay? Yes. Meaning 95% of one variable explains 95% of the what? Of the other variable. Then we have the R square. which is coefficient of determination. For this, you can see we have what? We have and that is a r squared of 91.76%, meaning it's a fairly good. We can say it is a fairly good model. But for more accurate model, we usually use a coefficient of determination of 95%. Okay, 95 or 98%, it is termed as good. But we can still say anything above 90, it's fairly what? It's fairly good. And then we have adjusted r squared. This is for now majorly if we were using or if we were doing for that is a multiple linear regression, we would have used what? We would have used the adjusted r squared more than what? The r squared. Then we have the standard error, that is the error term. The summation of all the differences between the data points and the line of best fit, okay, it is what? It is 3.5. And from the standard error, we usually conclude this. The smaller the standard error, the better the model. Okay? If we have a small standard error, it means that that is our data points don't have what? Don't have outliers. Like no data points which are far away from the line of best fit. Okay? Yes. So basically that's what it means. So that is the smaller the standard error, the good the model. Okay. And then basically observations, we add what? We add 24 observations. That is the count of our what? Of our data values for the 2 years with 12 months. You can see it is what? It's 24. And that's all about this class.